In this episode, we want to explore how word embeddings transform natural language processing, from simple statistical features to learned representations that finally captured meaning and context.
It's a fantastic topic because this transition wasn't just, a technical upgrade. It was a fundamental shift in how computers perceive human language.
A whole new philosophy, really.
Exactly. We moved from thinking about language as just a collection of symbols to thinking about it as a measurable geometric space of meaning.
Right. And to appreciate that shift, I think we have to start with where things were before. When we talk about teaching a computer to understand language, the original methods were, well, they were surprisingly blunt instruments.
That's a good way to put it. The foundational approach, what we now call classical NLP, was all about representing text using these sparse bag of words vectors.
Bag of words. Okay, so you're literally just putting all the words from a document into a big, unordered bag.
Pretty much. You convert a text document into a very, very long vector, where each dimension, each slot in that vector corresponds to a single unique word in your entire vocabulary.
And that vocabulary could be huge, right? Like 20,000 words.
Oh, easily. A standard data set like the Reuters News Corpus had nearly 19,000 distinct terms. So for every single document, you have a vector with 19,000 slots.
And you just put a number in the slot if the word appears?
You'd record its count, or maybe just a 1 to show its presence. But for any word that's not in the document, that slot is just a 0.
I see. And then there was a refinement on that, TF-IDF.
Right. Term frequency inverse document frequency. That was a clever way to weight the importance of a word. You'd take the word count, that's the term frequency, and then you discount it by how often that word appears across all the other documents.
So if a word is everywhere, like the or and, it gets less weight because it's not very special.
Exactly. It's not useful for telling one document apart from another. It's a great method for basic keyword counting, for search and retrieval.
But that world of sparse vectors obviously hit a wall. Where did it start to break down?
It had two really severe limitations. The first one is computational, and it's right there in the name. Excessive sparsity.
Sparsity meaning it's mostly empty.
It's almost all empty. Think about that 19,000 dimension vector again. Any single document, even a really long one, is only going to use a tiny fraction of the total vocabulary.
So most of those 19,000 slots are just zeros. It's an empty spreadsheet, basically.
And that's not just inefficient to store, it creates this huge mathematical problem we call the curse of dimensionality.
Okay.
When you have that many features or dimensions and your data points are so sparse, machine learning algorithms just struggle exponentially to find any meaningful patterns.
Because everything is so far apart in this huge empty space, it's hard for the model to connect the dots.
Precisely. It makes the models really prone to overfitting. It might learn something about a rare word from the one time it sees it, but it can't generalize that knowledge because the word's relationship to anything else is just too weak in that vast empty space.
Which brings us to the second, and I think the deeper limitation. It completely failed to capture meaning, didn't it?
Completely. If the model sees the word terrific once, it has no mathematical relationship at all to the word good.
They're just two different columns in the spreadsheet.
Two totally unique, mathematically unrelated dimensions. So good, splendid, spectacular. They were all treated as completely different things. The model only understood presence or frequency. It had no concept of synonymy.
Words with the same meaning.
Right. And it also couldn't handle polysemy, a single word that has multiple meanings.
Like the word bank.
The word bank, exactly. Is it a river bank or a financial bank? The model had no clue. It was just one dimension called bank.
So if a movie review used the word splendid instead of good, the system would see it as a fundamentally different review.
As different as good and zebra, they're orthogonal. There's no connection. And that was the critical failure. We realized we needed a way to encode the relationships between words, not just their presence.
Okay, so let's get into the conceptual shift that made that possible. We're moving away from just counting things to trying to find dense semantic meaning.
And the core idea that underpins this whole revolution is something called the distributional hypothesis. It was summed up beautifully by the linguist J.R. Firth way back in 1957.
What did he say?
You shall know a word by the company it keeps.
I love that. It frames meaning as a purely statistical thing. We don't need a dictionary definition. We just need to look at a word's neighborhood.
That's the entire idea. If two different words consistently show up surrounded by the same neighboring words, if they kept the same company, then they must be similar in meaning.
Okay, so give me a more concrete example of that.
Well, think about two people in an office, Alice and Bob. We see that Alice is always in meetings with the CEO, the head of finance, and the CTO. And we see Bob is also always in meetings with the CEO, the head of finance, and the CTO.
Right.
Now, even if we never see Alice and Bob talk to each other, the company they keep tells us they're probably very similar. They likely have similar jobs, similar seniority.
Their context is the same.
Their context is the same. And it's the same for words. If cat and dog both show up near words like leash, vet, and food, then their representations should be neighbors in this new space we're trying to build.
So the goal became to stop using these massive, empty vectors and instead create compact, dense, low-dimensional vectors.
That's the shift to distributed representations. Instead of tens of thousands of dimensions, we're trying to compress all that semantic information into, say, 100 to 1,000 dimensions.
And in that new, smaller space, words with similar meanings should be mathematically close together.
President Reagan and Bush should all have similar vectors because their contexts overlap so much. They should cluster together.
Now, this idea of creating dense representations wasn't totally new. There were some earlier models that were already trying to do this, especially in topic modeling.
Absolutely. The field had been working on this for a while. The most well-known models were latent semantic indexing, LSI, and especially latent Dirichlet allocation, or LDA.
LDA was huge. The idea there was that any given document is really just a mixture of a few hidden topics.
Right. It's a generative probabilistic model. It tries to figure out the probability of a word belonging to a certain topic and the probability of a topic being in a certain document.
So how did that give you a dense vector?
The topic mixture itself becomes the vector. If a document is, say, 80% about medicine and 20% about public policy, that 80-20 split is its new, compact, dense representation.
And that was a workhorse for a long time, right? Analyzing medical research, legal
A
documents.
massive workhorse, but it had one major problem.
It was slow.
It was a beast, incredibly slow. These models had to iteratively search for the best possible set of topics. It wasn't a single calculation. It was a long process of adjusting and recalculating over and over again.
Taking hours or even days on standard data sets.
Exactly. And that bottleneck made it impractical for the massive web-scale data that was starting to become available. The pressure was on to find a way to get these dense semantic representations, but to get them fast.
This is where we started to see some interesting engineering solutions pop up, like one called DCOT.
Right. Dense cohort of terms. That was a really clever bridge. It was an unsupervised algorithm that tried to map those sparse vectors into dense ones by essentially translating rare words into more common, similar words prototype terms.
And how did it do that so much faster than something like LDA?
It was inspired by something called a denoising autoencoder. The idea is you take a document, you artificially break it by removing some common words, and then you train the system to reconstruct the original to fill in the words you took out.
Okay, that makes sense.
But the key innovation was a mathematical simplification they found. They figured out a way to get to the answer directly using linear algebra without having to do the slow, iterative breaking and fixing step over and over.
So instead of a slow search, it became a direct calculation.
A massive difference. It cut the training time down from hours to minutes, sometimes even seconds. It proved that fast, scalable semantic learning was actually possible.
The stage was perfectly set. Everyone wanted speed, scale, and meaning. And then, around 2013, the true paradigm shift happened, the one that democratized all of this.
Word2Vec from Google. This was the pivotal moment. It delivered incredibly high-quality, dense vectors at a speed nobody had ever seen before, using a really simple neural network.
So what was the big idea? What made it so much faster and more effective than those earlier models?
It used a very shallow neural network, just 2 layers, and here's the key. It wasn't trained to classify documents or find topics. It was trained on one simple task, predicting words. The dense vectors we wanted were just the internal weights the network learned in order to get good at that prediction game.
And there were 2 main ways it played that game. The first one was continuous bag of words, or CBOW.
CBOW is the fill-in-the-blank model. You give it the surrounding words, the context, and you ask it to predict the word that's missing from the middle.
So the cat sat on the May, and it has to predict Matt.
Exactly. It's learning what word is most probable given that neighborhood.
And then Skipgram just flips that challenge on its head.
Right. Skipgram is the what else is there model. You give it one word from the center, like cat, and you ask it to predict the words that are likely to be its neighbors.
So given cat, it might predict the sat, on, and mat.
Precisely. And they have slightly different strengths. CBOW is generally a bit faster to train, but Skipgram is known to do a better job with rare words because it gets more training updates for each individual word.
So we're learning these dense, say, 300-dimensional vectors super efficiently on billions of words. But the real magic was what we found inside the geometry, that new vector space.
This is the most famous part of Word2Vec, the ability to do vector arithmetic. It proved in a really tangible way that the model had actually captured meaning.
You have to tell us the king and queen analogy. It's the example that really makes this click for everyone.
It really is. So you take the dense vector for the word king, then you mathematically subtract the vector for man, and then you add the vector for woman.
Okay.
The resulting vector, the answer to that equation, points to a location in the space that is closer to the vector for queen than to any other word.
So vector of king minus man plus woman equals queen. It's like it isolated the concept of royalty and the concept of gender as actual directions in this space.
It's genuinely profound. It showed the model didn't just learn that king and queen were similar, it learned the relationship between them, the analogy. And this worked for all sorts of things, like verb tenses walking to walked was the same direction as swimming to swam, or country to capital city relationships.
Word2Vec just became the default overnight. But the field was moving so fast. A year later, in 2014, a competitor emerged from Stanford.
GloVe, or Global Vectors for Word Representation. The idea behind GloVe was to try and combine the best of both worlds, the local context prediction of Word2Vec with the global statistics of the older methods.
So it wanted the speed and power of the new neural models, but with the statistical rigor of looking at the whole data set at once.
Exactly. Instead of learning implicitly through a prediction task, GloVe trains directly on the aggregated global word-word co-occurrence statistics from the entire corpus.
Okay, what does that mean in practice? What are co-occurrence statistics?
And it's just a giant table of how often every word appears near every other word in the entire data set. But the key insight for GloVe wasn't the raw counts, it was the ratios of those counts.
Why are the ratios so important?
Because that's where you find the fine-grained meaning. Let's take the example of ice and steam.
Okay.
Both words are related to water, so they'll probably co-occur with the word water a lot. But the difference is revealed when you look at words like solid or gas.
Right. Ice is solid. Steam is gas.
Exactly. So the ratio of how often ice appears near solid versus how often steam appears near solid will be very high, and the ratio with gas will be very low. GloVe's training objective is to learn vectors that directly reflect those powerful ratios.
So if two words relate to the rest of the vocabulary in the same statistical way, their vectors have to be numerically close.
That's the objective. It's a really elegant, statistically grounded approach. And it achieved results that were just as good as Word2Vec, and sometimes even better. It proved there was more than one way to capture that distributional hypothesis.
So this era gave us these amazing, high-quality, dense vectors. But both Word2Vec and GloVe still had a big, shared, practical problem. The out-of-vocabulary problem.
A huge barrier. They are completely bound by the vocabulary they were trained on. If you're running your system and you encounter a rare word, a new brand name, a typo,
A word it's never seen before.
it just fails. It has to assign a random vector or a vector of all zeros, which is basically useless. For specialized fields like medicine or law, where new terms pop up all the time, this was a critical flaw.
And this flaw led to the next big conceptual jump, which was subword modeling. This came from FastText, out of Facebook AI research.
FastText changed the fundamental unit of analysis. Instead of treating the whole word as the smallest piece, it broke words down into a bag of character engrams.
The subwords, it's looking at smaller pieces of the characters inside the word.
Exactly. The word unbelievable is no longer one single indivisible thing. It's treated as a collection of its parts, like unbelieve and able.
And the final vector for unbelievable is just the sum of the vectors for those little pieces.
It is. And this simple change had two massive benefits. First, it automatically captured morphology, the internal structure of words.
Meaning that related words like run, running, and ran all share that run component, so their vectors are naturally similar.
Yes. The model understands the relationship without being explicitly told. But second, and most importantly, it basically solved the out-of-vocabulary problem. Because even if the model has never seen the full word microblogging, it has almost certainly seen the subwords micro, blog, and ing. So it can construct a pretty good, meaningful vector for the new word on the fly.
That makes the whole system so much more robust to real-world messy text.
Incredibly robust. And while FastText was doing this at the character level, other researchers were taking word-to-vec vectors and using them to represent short phrases or n-grams.
So this tackles the problem where just counting not and good separately misses the point of the phrase not good.
Precisely. For a task like sentiment analysis, that's crucial. Researchers would create a vector for not great by averaging the pre-trained vectors for not and great. Then they'd cluster these phrase vectors into what they called semantic concepts like strong negation.
So a document becomes a bag of these meaningful concepts, not just a bag of words.
And that proved to be dramatically more effective for classification tasks. It was another step up in capturing linguistic nuance.
The revolution seems complete at this point.
Right.
We have speed, we have meaning, now we have robustness. So let's talk about the impact. What did this unlock for the field?
The gains were just dramatic across the board. Performance on almost every NLP task skyrocketed because our models could finally generalize based on semantic similarity. They weren't reliant on brittle, handcrafted rules anymore.
So for sentiment analysis, what did that look like?
You saw accuracies on things like movie review classification jump up towards 90% just by feeding these embedding features into a simple classifier. The features themselves were doing all the heavy lifting. The model moved beyond counting positive and negative keywords to actually understanding the meaning of the review.
And this would apply to any kind of document classification, I'd imagine.
Yeah.
Identifying legal documents, financial reports.
All of it. It also completely reinvigorated topic modeling. People could now use these high-quality representations to power much more sophisticated versions of models like LDA.
So LDA didn't disappear, it just got a massive upgrade.
A huge upgrade. It became essential for making sense of massive, complex data sets. In medicine, people used it to find hidden topics in millions of research articles or patient records.
A way to find the signal in all that noise.
For sure. And in social media analysis, it was foundational. You could use it for things like hashtag recommendation or for tracking shifts in public opinion by seeing what topics were bubbling up in real time.
And I assume search and ranking got a lot smarter.
Oh, completely transformed. Before, you needed an exact keyword match. With embeddings, a search engine could understand that your query for, say, ways to fix a leaky faucet was related to a document that talked about plumbing repair.
Because the vectors for faucet and plumbing would be close together.
Exactly. It made the whole experience much more intuitive and forgiving.
So word-to-vec, glove, FastText, they were the backbone of NLP for the better part of a decade. But this entire era, this whole approach, was still held back by one final critical limitation.
The problem of static ambiguity.
Static, meaning the vectors never change.
They never change. Once the model is trained, every word gets one single fixed vector, regardless of the context it's used in.
And this brings us back to the bank problem.
It's the perfect example. The model sees bank in sentences about money and finance, and it sees bank in sentences about rivers and geography. So the one single vector it learns for bank ends up being a compromise.
An average of all its meanings.
Right. It gets diluted. It's not perfectly financial, and it's not perfectly geographical. It's just a blurry average somewhere in the middle. The model can't handle homographs words with the same spelling but different meanings.
And that loss of precision, that inability to handle multiple meanings, was the final wall they hit.
It was. For truly complex tasks like high-quality machine translation, you need to know which bank you're talking about. The vector for bank needs to be able to shift, to move around in that semantic space depending on whether its neighbors are money and loan or river and erosion.
So this is what sets us up for the modern era of NLP. The static embedding revolution laid the foundation.
A critical foundation. Those dense vectors were the necessary input. They proved meaning could be learned and represented numerically. That set the stage for designing new architectures whose entire job was to inject context into those vectors.
And this is the lineage that leads us straight to the huge language models we have today.
Exactly. First, those static embeddings were fed into what we call recurrent neural networks, or RNNs. They tried to read a sentence word by word and keep a running memory of what they'd seen.
But they had trouble remembering things for very long.
They did. They struggled with long-range dependencies. That led to the development of LSTM's long short-term memory networks, which had much more sophisticated memory cells.
So they could remember context from much earlier in a sentence.
For much longer, yes. And that constant push to better manage context eventually led to the idea that changed everything.
Attention.
The attention mechanism. It allowed a model to look at the entire sentence at once and decide, for any given word, which other words in the sentence were most important for defining its meaning in that specific context.
So that's the full path. Embeddings gave us the meaningful starting point. RNNs and LSTMs tried to add sequential context. And attention finally figured out how to make that context dynamic and flexible.
And that whole chain of innovation is what culminated in the transformer architecture, which is the foundation for models like BERT and all the modern LLMs. That was what finally solved the static ambiguity problem.
So what does this all mean for the listener? The core lesson here seems to be the immense magnitude of this transition. We went from just crudely counting words to creating these rich maps of meaning.
And discovering that relationships like kin minus man plus woman equals queen were actually encoded in the geometry of that map. That was the breakthrough that unlocked huge gains in everything from sentiment analysis to scientific discovery.
And the ultimate failure of those static maps, the bank problem, is precisely what drove the entire field forward into the current era of truly contextual models.
It is. And it's important to remember that even today's huge models still rely on that core idea. You first have to represent language in a dense, continuous mathematical way before you can start making it dynamic. The static embedding models took that essential first step.
The ultimate challenge was making those distances in the map change based on the specific sentence they inhabit. Next time, we'll move on to those architectures, the RNNs, LSTMs, and the world-changing power of attention that figured out how to make a word's vector change depending on its context.
Thank you for joining us on this journey through such a technically intricate yet fundamentally human subject.
Thanks for listening to the Adaptix podcast. If you have any questions,